In the previous video, we'd looked at the Nyquist-Shannon sampling theorem, and if you haven't checked that one out yet, I encourage you to do so now, since this entire video will be based on the previous one. As a refresher, the sampling theorem states that a band-limited continuous time signal can be represented in its samples and can be recovered back when sampling at a frequency greater than twice the highest frequency component of the input signal. Alright, let's apply this principle to audio signals. And we can already identify and limit the highest frequency component that should be in our input signals. It's the limit of human hearing, 20 kHz. It's an optimistic limit that's been established through a lot of research and testing of individuals in the general population, but for a majority of us, it's well below that. And as you grow older, your sensitivity to high frequencies decreases. We can realistically cap the highest frequency in our input signal to be 20 kHz, because having any frequencies above that is just wasteful and unnecessary. According to the sampling theorem then, our sample rate can be any value over 40 kHz. And as mentioned in the previous video, we need a bit of a buffer between the highest representable frequency and half the sampling rate, or the Nyquist frequency. And we came up with a practical estimate of choosing a sample rate which is around 2.5 times higher than the highest frequency. We did this in consideration of the practical limitations posed by analog filters when cutting off frequencies above the Nyquist. This number is not a hard rule, but rather just a suggestion, a ballpark number if you will, and is solely dependent on the hardware you're using. Well-engineered and well-picked electronic components and converters are more than capable of handling tight spaces for filter cutoffs. In contrast, poorly designed circuits would need even more bandwidth than the estimate of 2.5 times to fully attenuate the frequencies before the Nyquist. So what do we have that we can work with? What sample rate can we use which is close to 50 kHz, which is 2.5 times 20 kHz? Some of the popular and most commonly used sample rates include 44.1 kHz, which gives us a buffer between 20 kHz and 20.05 kHz, which is the Nyquist frequency for the sampling rate of 44.1 kHz. The buffer, or the guard band, is 2.05 kHz of bandwidth for the filter to achieve its full attenuation, which is admittedly a bit tight. The next common sampling rate is 48 kHz, which gives us a decent bandwidth of 4 kHz to work with. After that is 96 kHz, which is almost double what we initially wanted, but it does have a very comfortable 28 kHz of bandwidth. What does bandwidth mean here exactly? In the context of signals in general, it means a range of frequencies. Take 44.1 kHz sampling rate for example. This sample rate can theoretically represent frequencies from 0 Hz to 22.05 kHz. Its range, or bandwidth, is said to be 22.05 kHz. But bandwidth in the context of transmission has a slightly different implication. Signals can be propagated through guided transmission media, such as cables and optical fibers, and wirelessly through electromagnetic waves in the form of radio and microwaves. These transmission media have a certain bandwidth associated with them as well. But in this context, it's the maximum rate at which information can be flooded through the medium. You can think of it as information rate or data rate. This rate has a tendency to affect the choice of audio bandwidth that we select, but is generally dependent on the application. For example, if you want to transmit audio to your speakers through an amplifier in your own home, even conventional copper cables like coaxial cables have a bandwidth of several hundred megahertz. When comparing that to even the most generous sample rates chosen for audio, transmitting multi-channel audio through these cables is a breeze, with a lot of bandwidth to spare. Let's look at a different application in telecommunication: phone lines. The telephone audio signals are usually passed through copper cables with really high bandwidths when compared to audio bandwidth, like we already found out. But you're not exclusively using this line. Thousands of people could be utilizing the same phone lines for communication simultaneously. Over here, you don't have the luxury of choosing a generous, high-fidelity sample rate. Efficiency is key. Going back to our conundrum of choosing the right sample rate, we can agree that we want all the audio frequencies to be represented, right from 20 Hz to our hearing limit of 20 kHz. But do we really? Yes, if you want to listen to Beethoven in all its high frequency glory, but if you just want to talk to somebody on the phone, researchers discovered that intelligibility of human speech lies between 300 Hz and 3.4 kHz. So, to be clear enough for another person to understand your speech, 3 kHz of audio bandwidth is generally sufficient. All the higher frequencies can be ignored. So you don't need a high sample rate to express just 3 kHz. A sampling rate of 8 kHz should do just fine. Do you want to know what 8 kHz sampled audio sounds like? This is exactly it. You can hear that all the high frequencies are missing, but it's still quite intelligible and recognizable. It sounds like I'm talking through a telephone line, because this is precisely the frequency that telecommunication engineers use for sampling. I'm back now on the full audio spectrum bandwidth. With 8 kHz as the sampling rate, we have a tight guard band between around 3.4 kHz to the Nyquist frequency of 4 kHz. So it's harder for analog filters to completely cut off within this range. But again, in telecommunication, efficiency is more important than producing the best audio quality possible. Telecom engineers generally prefer efficiency and low-cost design, and can tolerate a bit of aliasing distortion produced due to low filtering performance during conversion. If you're still confused as to why low sampling rate means high efficiency, think about it in terms of the amount of data we have to deal with every second. With an 8 kHz sampling rate, we are looking at 8,000 data points per second that we have to create from the analog signal, to transmit along a cable, to store, and to replicate. As the sample rate increases, the converters would have to work faster to create more data points within that same 1 second interval. Their processing speed would need to ramp up, storage capacity would need to increase, and generally all the components within the signal chain would need to handle the high rate of data flow. Over time though, as processors became faster and as transmission media became more efficient, we could afford to sample higher. I want to devise a simple experiment. Let's go to Audacity, and this time we'll record something on it. I'm using a Focusrite audio interface and an Audio-Technica condenser microphone, which are very capable audio devices. But I'm intentionally setting the sample rate to a low 8 kHz while recording. I'll play a sinusoidal sweep of frequencies from 200 Hz to about 10 kHz on another device. You could see and hear that the audio capture of the sinusoidal sweep ended in the middle, while the sweep continued. This should be fairly comprehensible by now, since the analog to digital converter in the Focusrite cuts off any frequencies above the Nyquist frequency of 4 kHz. Analyzing the waveform, that's what you see as well. If you select the track and head over to Tracks and Resample, you have the option to change the sample rate now, post-recording in the digital domain. Obviously, choosing a high sample rate now would not bring back the missing high frequencies, because they were never recorded to begin with. But you have extended the capacity to hold more bandwidth. This could come in handy when you want more bandwidth to play with. For example, I can choose to pitch up the recording. Let's select the track, go to Effect, and change pitch. Over here, I'd like to increase the percentage change to 100%, which is essentially increasing the pitch by an octave. I'll also turn on high quality stretching to avoid any aliasing. And I'll set the project sample rate higher up so we can hear the change. Since I have chosen to resample at 44.1 kHz, we have a lot of bandwidth available to us, and we can represent the shifted high frequencies. Now let's select the track and resample it again, but now going back down to 8 kHz. This time the resampling process recognized that there were frequencies higher than the Nyquist and just cut them off. We are back in a position where we have no spare bandwidth to represent them, so the higher frequencies above 4 kHz just vanish. In this whole experiment, I want you to recognize that the sampling and filtering occurred in both domains. Firstly, in the analog domain to convert the microphone signal to a digital signal using analog equipment and an analog low-pass filter. And then again in the digital domain when we resampled the track and made use of a computer program and an algorithmic digital low-pass filter to do exactly the same. In both cases, the output was consistent and predictable. I also want to highlight the importance of choosing the right initial sampling rate for recording, because you can't recover frequencies that were skipped for being higher than the Nyquist frequency. Going back to our discussion, another commonly used sample rate is 16 kHz, and it sounds like this. It's generally used in voice over internet protocol applications like Skype and WhatsApp, which represents an 8 kHz bandwidth of audio frequencies, which sounds much more crisp than the previous sample rate. Again, the primary motivation here is to keep the sample rate low enough to transmit these signals in conditions when internet connectivity is poor, but high enough to capture more frequency content in general. At 44.1 kHz, the rate at which my voice was originally recorded at, we have a full representation of all audible frequencies. If you ignore the filtering difficulties during conversion, with a 44.1 kHz sampled digital signal, you've already achieved the highest audio fidelity possible. The number 44.1 seems very specific. It was developed and standardized by Sony and Philips along with their invention of the compact disc. The number was chosen to work well for mathematical conversions when working with different video frame rates, and also to keep the size of the audio recording slim to fit well into the limited space offered by CDs. 48 kHz is another common sampling rate, predominantly used along with video, again for its easy and whole numbered mathematical conversions when working with different video frame rates. It's quite likely that the streaming service that you're watching this video on had resampled my audio from 44.1 kHz to 48 kHz when the video was uploaded, and you're listening to a digital 48 kHz rendering of the audio. For consumption of audio, for listening and playback, having sample rates higher than this is just wasteful and unnecessary, since it adds no value in terms of audio fidelity in the audible range of frequencies. It would only bloat up the overall bandwidth of the digital signal. So is that to say that high sampling rates are absolutely pointless? Not at all. Again, as a consumer of audio and even as a producer or sound engineer, in most cases, a sampling rate of 44.1 kHz or 48 kHz is ideal, and you would never need more. But if you are interested in hardware design or signal processing or into building applications and writing plugins, you're likely to use higher sampling rates by means of oversampling in the digital domain. This is generally done to deal with the problem of aliasing. That's predominantly where high sample rates are used. I can think of one other example where you want to record wildlife sounds like the ultrasonic frequencies emitted by bats, for example. Of course, in this case, you need more than just a high sampling rate. You need specialized equipment for capturing ultrasonic frequencies. But this is too specialized a case, and we won't be delving into it. But the conversation inevitably retracts back to what analog to digital converters are capable of. Are they truly capable of converting analog signals to digital signals at 44.1 kHz sampling rate with all the difficulties of filtering that I've been waffling on about? Yes, they are. and I'll waffle on a little more about how that's actually possible and the innovative ways that engineers have devised to circumvent the analog filtering problem. But first, a little bit more about why filtering at the input stage is needed to begin with. For this, we need to look at aliasing in further detail.